So the goal, so we know at this point, we want to use the auxiliary file as the search on the original table. The original table, at this point, we imagine the table size is very large. So if we use the linear search, extremely slow. So we want to greatly speed up the search operation. To do that, we have to rely on some special structure to allow us apply the binary search. We know binary search can do much faster than the linear search. So for that reason, because we cannot touch the original table, we have to preserve the business data in the original form. We don't want, in order to make the business people feel comfortable on the original data, so we cannot do any on the original data. And we just create some supporting data. Okay, it's hidden. The business, the supporting data, they do not even realize. But when we work on the supporting data, we can apply binary search because we can sort data in the index files. So that's the the background. Then we move to this primary index topic. Now we need to get to the how to design the structure of these index files. All right. So now we need to consider the order of data. Because at this point, order information is important to help us make a decision. How to build the structure of the index files. So the order information is an important consideration. All right. So here, let's look at these two cases. All right. Because here, when we create an index file, we look at a specific index field, right? Yeah. So regarding specific index field, here, let me draw. So this is original table. Yeah. There are many fields in original table. Yeah. In order to do search, we need to provide a search key, right? The search key is for a specific field. Yeah. So this field is the indexing field. Indexing field. All right. Now we consider the order information for the indexing field. Okay? Yeah? So there are two cases. The first case, the indexing field is ordered. The second case, unordered. Yeah. Because based on these two properties, the structure. Yeah. So important. Okay. All right. For the first case, the indexing field is ordered. That means it's ordered in the original table. Okay? Yeah. That possible, that could happen. In case it happens, then we can take advantage of this ordered property. Waste it, right? Yeah, the original search field, the data is already ordered based on this field. Yeah. Although here, in general, actually the probability of this situation is not high. Of this, usually it's not high. But if it happens, then we can take advantage of this order to help us speed up the search. All right. Yeah. Because in this case, in our index file, the key field in our index file, we do not need to do the sort, right? We do not need to sort, yeah, because already ordered. So no sorting needed, right? Yeah, no sorting needed, yeah. All right. Then we can apply the binary search on the ordered field directly, right? Yeah. So this case corresponds to our primary index case. Yeah. If we have this property, then we will build the primary index. Okay, all right. Then the second case, unordered. That's different. Unordered. Yeah, because apply binary. So you have to sort it first. You need to do the sorting before you build the index file. To make it ordered, you need to make it ordered in your index file. Yeah. Then you can apply binary search. Yeah. All right. So then, in this case, you can also build a binary search-based index, but this time you cannot use the primary index. Okay? Yeah. So you have secondary index. Yeah. And later, I will talk about the special structure of this kind of indices. That's we call a dense index. Dense index. Okay, the primary index, not a dense. Okay, the primary. Yeah. So what's the meaning? We will see later. The primary index, opposite of the dense index, the sparse index. Sparse index. Can see some property, dense and sparse. You can see some property, yeah, yeah, because you know the meaning, the difference of these two words. All right, sparse, yeah. You do not need to store the information of all the rows. You can jump. You can store the position of the row information in a sparse way. Okay, not dense way. Dense way means you need to store the location information for all the rows. That's the dense way. Okay, you cannot miss one. Yeah, sparse way, you can save. Skip, because based on the given ordered info, the property, you can deduct. You can make a deduction. You can use your deduction to derive the location information. Then you can skip the location information of many rows. In that way, you can save to make. So that's two ideas I want to explain in this part 2 of part B. Part of the part B. All right. Now let's look at the primary index first. We study the dense index second. Okay. All right. Now, the structure of the primary index. All right. From the high level, so the same structure as in the general index file, but there is one important property. That the first field of the same data type as the ordering key field of the data file. All right, so that's the same as the index file. Right? But the second property, it's a special property. The second field is a pointer to a disk block. I need to explain the structure of disk block later. Okay? To a disk block that contains the record to be searched for. So here, pointer. So here you can see pointer to a disk block. This pointer does not point to the location of one particular row. It points to the location of that disk block. That's the key difference. Okay? So if we want to talk about the main property of this primary index, this is the main property. Okay? Point to the disk block. All right. So then I will explain this. Why we can point to disk blocks to locate the individual rows. All right. It's a long story. Okay. All right. So then, when we look at the number of index entries, this property, we have this property. There is one index entry, index file for each block in the data file. Okay, one-to-one correspondence. There is a one-to-one correspondence, between index entry and disk block. That kind of one-to-one correspondence. Okay? So from this one-to-one correspondence, you can sparse. It is not dense. Okay? Why it is sparse, not dense? So what is the dense case? Here, let me explain the dense case. For the dense case, there is also one-to-one correspondence, but between what? One-to-one correspondence between index entry, one index entry corresponds to one row. Okay? One row in the table, original table. Okay? So if you have the one-to-one correspondence like this, each index entry corresponds to each row in the original table. Because in this way, we do not skip any row. Okay? No row is skipped from the original table. dense. Yeah. In this, one entry corresponds to one disk block. We skip many rows. Why? Because each disk block can contain multiple rows. All right? Yeah. Each disk block contains many rows. Okay? Yeah. Many rows. Yeah. Dozens of rows. Yeah. Usually. Yeah. Many rows. But for those dozens of rows, we only need to pick one as the representative, one special row as the representative. Okay? So we use our index entry to point to that the disk block, the whole disk block. Yeah. One representative. The remaining rows in the same disk block, we do not need to use any index entry to point to those rows. Then we can save. Okay? Yeah. So that's why we call it sparse index. The primary index, take advantage of this ordered data. Yeah. Make good prediction if we skip information for all those rows, but we can easily recover easily. Later I will explain how to recover. Okay? Yeah. But if the data is unordered, the original data is unordered with respect to the indexing field, then we cannot make prediction. All right? Yeah. Because unordered, how can you make prediction? Ordered, yeah, we can make good prediction. If we cannot make good prediction, we have to store the location information for all the rows. That's why we have to use the dense index. That's the logic. Okay. All right, so after you understand this logic, then I explain the detail, okay, regarding the disk blocks. All right. Next, anchor record in primary. This time, I need to draw a diagram for the disk block structure. All right. Then you can understand how do we store the rows in each disk block. Yeah. All right. Each index entry has the value of the primary key field. Yeah, so I talked about primary key field last time. Okay, yeah. Do not get confused. Yeah. This primary key is different from our previous primary key. Meaning, yeah. Meaning is different. Yeah. All right. Primary key field for the first record in the block. Anchor, yeah. So that is the concept of the anchor record. So what is the anchor record? First record in the block. That's the anchor. So that's what I call the representative. Okay? There are many records in one disk block, but we just pick the first one as the representative for all other disk blocks because it's enough. The location information for the first record is enough to help us make prediction for the location of all the other records. Yeah. So why? Let me draw a diagram of the disk block concept. Yeah. So we need to zoom in. Yeah. Now we need to look at a hard drive. Our hard drive, the structure of our hard drive. How do we store our data on the hard disk? Yeah. All right. Just you know, some simple understanding here. Yeah. All right. So our hard disk has the form. So we use cylinder. Okay. Yeah. So this cylinder represent hard disk. Yeah. All right. Yeah. All right. So in this cylinder form of the hard disk, there are, so this cylinder contains a stack of disks, right? Yeah, stack of disks. Yeah, yeah. So 1, 2, many disks stacked in this cylinder. Okay, a stack of disks. So we can store data on all the disks in the cylinder. Okay, all right. Then let's just take one disk out of it and look at its structure. One disk, you know. All right, one disk. This one disk has two surfaces. Okay, two surfaces. And we can store data on both surfaces, right? Yeah, two sides. Yeah. Storage, two sides. Yeah. All right. Let's just look at one side. Yeah. Okay. So in one side, we divided the space, the area of this disk in multiple concentric circles. Concentric circles. So there is a center, okay? Then we, you know, draw many concentric circles. Yeah. All right? Yeah. Okay. Yeah. So each circle, yeah, so we call it a track. Okay. Yeah. Yeah. So we store the data on all these tracks one by one. Okay. Yeah. 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 We organize in this way. All right. Then we further divide all these tracks into sectors. Okay, all right. Like this. All right? Yeah. All right. Sectors, like that. Okay, yeah. All right, yeah. Yeah, so you can see. Yeah. Then, let's look at each sector. Yeah. Arc. It has the arc form. Okay, yeah. So that arc form, we store the data. Look at one sector for one particular track. Okay, all right. Yeah, like that. This arc. Okay. Yeah. Then on this arc, we further divide this arc into multiple disk blocks. Now we get to the unit. Each disk block we treat it as storage unit. Okay, all right. So disk block, a sequence of disk blocks along this arc. Okay, yeah, like that. Okay, yeah. So this one disk block. Yeah. Then, now, because this is our storage unit, yeah. Okay? Yeah. So this is our storage unit. Okay, all right. Yeah. So we can use these disk blocks to store. All right. What do we store here? Okay, all right. The data in these two forms. Okay, all right. Original data. Data in the original table, right? Original data and index files. Index files, we store them in these disk blocks. Okay. All right. So with that picture, now we can discuss, one-to-one correspondence. Okay. Yeah. Then another information you may like to know, yeah, because when we talk about the storage unit, so for each disk block, what is the typical size, right? Yeah, typical size. The typical size is 4 KB, 4 kilobytes, 4 KB. Yeah. Okay. Yeah. So then, why we call it storage unit? Because the data stored in each disk block is used as a unit when we load our data into the main memory. We need to load the data into main memory. Okay, all right. Load it. Load the data in each disk block. One each time. Okay? Each visit, you load one disk block of data into the main memory. Okay? Yeah. So that's why this concept, this unit concept is important. Yeah. One page. Yeah. So you load one page. Yeah. Just like a page. One page of data into the main memory. So one unit. This much. Okay. All right. Appropriate data size. If the size of each disk block is too small, then not efficient. Yeah. Because every time hard disk is relatively slow, right? Yeah. It is relatively slow. So if you only load too little data, then you waste your trip, right? Yeah. The trip is relatively expensive. So you want to carry relatively more data. But you cannot in the hardware design, when you send your data, the bus, bandwidth of the data bus, there is a bandwidth limitation. Yeah. If your data size is too large, you need to split it. You need to send it multiple times. So then, it's not efficient. You need to split anyway, right? Yeah. So then you just small, send one block of data to the main memory easily. Yeah. without breaking. You don't need to break this disk block. Okay? And you do not, you make the size of this disk block large enough to carry enough data. Yeah. So for that consideration, yeah. So this size is the most popular size. Yeah. All right. Yeah. So you load into the main memory, load the data. One block each time, each visit, load one block. Okay. Yeah. So into main memory. Yeah, into main memory. Yeah. After you load it, then you can search the disk block in main memory that much faster, right? Yeah. No, to search the data in main memory much faster than search the data in the hard drive. Yeah. The ratio, last time I gave you approximate number 1 to 100. The time used ratio, approximately 1 to 100 ratio. Okay? Yeah? So then you don't worry. When you search the data, the linear search. Okay? Search or binary search. Okay? Yeah. Linear search, you don't worry, yeah, because it's so fast. First, the disk block size is not very large. 4 KB. Or in 4 KB area with just 1/100th of the search time in the hard drive, then you don't worry about it, right? Yeah, even linear search, you can do it very fast. Yeah. All right. Yeah. So that's the background information before we get to the structure of primary index. Yeah. We have this background picture in our mind. Yeah. Then we can continue our discussion. Each disk block usually contains multiple records. Yeah, so I already talk about that. Yeah, multiple records. Yeah, 4 KB. Yeah, the size of hundreds of bytes, hundreds of bytes. Then you do division. 4,000 divided by several hundreds. Okay, the size of one record. So usually hundreds of bytes. You do division, you have, certain number, dozens. That's why I said dozens of records you can store in each disk block. Yeah. All right. It is, so here, this first record in the disk block is called anchor record. Okay? Yeah. First record. Anchor. Because the location of the first record gives the location of this disk block, right? Yeah. So, because the location of this anchor record also gives the location of this disk block. Okay? When you have the location of this disk block, so yes, okay, yeah. Location we number representing address on the hard drive. Yeah. After we have the address of this disk block, we can load the whole block into main memory, right? Given the address of this disk block, every time we load the whole disk block into the main memory. All right. All right. a primary index only stores the field values for block anchors. Yeah. So this is the main property. This is the main property of the primary index. Yeah. So I already explained before, but I need to explain a little more. Yeah. Primary index, we only store the locations of the anchor records. Other records, we do not. For non-anchor records, we do not need to store their locations. Okay? Yeah. Yeah. Why? Yeah. So yeah, I can explain why. Yeah. So I use the space here. Okay. All right. Suppose this is the one disk block. Okay. Yeah. Yeah. One disk block. Okay. The first record in this disk block, this is the anchor record. Okay, this is the anchor record. Other rows start in this non-anchor record. Okay, all right. Yeah. Why do not need to store location? Because every time we load the whole disk block into memory. Yeah. So if we can make a prediction, because if we know this disk block is the right one, okay? If we know this disk block is the right one, yeah. For example, suppose your data search is targeting on this particular rows, okay? This particular rows, yeah. By the ordered data information, you can predict the data to be searched is in this particular disk block. Yep. So the binary search, when you do binary search, you can easily find the right disk block to load. Then you just load the whole disk block, containing your target row in that block into the memory. Then you do the search in the main memory, you can find it. Okay. So the reason you do not need to store the location for the other rows, because you can make good prediction. The targeting row must be in certain disk block. How? Binary search. Later, we will get there. Later we will talk about that. Find the right disk block. And based on the original order information must be true. Okay? Then we just know the whole disk block of data. Then our target row must be there. Yeah? That's the reason we can save. We do not need to store the location for all the other rows, non-anchor rows. Yeah, we can save a lot of storage space. Yeah. So that's the reason. All right. Now we can understand this property. All right. The total number of entries in a primary is the same as the number of disk blocks in the ordered data file. One disk block, you only need to have one entry. Yeah. So the total number of disk blocks, you have the same number of index entries for your primary index. Yeah. Now it's very easy to understand. After all the background information given, yeah, now you can understand this property. Okay. Yeah. So this number usually smaller than the number of records. Yeah, much smaller. Yeah. You can see this number is much smaller in the original file. Yeah. So how small here? Let me use a simple way to describe this how smaller this number is. All right. It depends on how many rows you can store in one disk block. Okay? Yeah. Here I just use a few simple examples. If you can store 20 rows in one disk block, then this number, this number means the entry number, index entry number. Okay? So this number means the index entry number. This number, so what's that? This number of entries, index entries. Okay, so this number, If there are 20 rows in each disk block, then this number is 1/20 of the number of records in the original table. Okay? 1/20. Yeah. If there are 30 stored in each disk block, then this number is 1/30 of the number of records in the original table. Yeah. So every 30 the anchor record you pick as the for all the 30 records in the same disk block. Yeah. That straightforward understanding. Okay? Yeah. Yeah. So in that way, you can see we make the number of index entries in primary index much, much smaller. Yeah. When we apply binary, so here you can see why people, if you can use the primary index, then you should use it. Yeah, because so there are two improvements here. Yeah. All right. So then, the first improvement, entry size. Entry. Each entry has a size, right? Yeah. Then another is the record size. Each record, there is a size. Yeah. We know entry size is much smaller than the record size, right? Entry size, you only have two fields. The key index key field and the pointer field. Original record size, many fields. Okay, yeah. So usually index size, much less than the record size. Second, the number of index entries is 1/20 or 1/30, like that. That the number of the original record numbers. Yeah, another reduction. Okay, so you have this two reductions. Yeah, so now you apply binary search on a much smaller primary index file, and you use number of comparisons. Yeah, so that's the improvement. Yeah. Good improvement here. Yeah. All right. So here we cover pretty much the basic things of the primary index. All right. Performance of primary index. Yeah. Now I can talk about the binary search part. The size of the primary index file So there are fewer index entries than there are records. Yeah. So the 1/30th, 1/30th. So in that level. Okay. Yeah. Each index entry is typically smaller. Yeah. So I just explained than the data record because it has only 2 fields. Yeah. All right. More index entries than data records can fit in one disk block. Yeah, another property. Because we use the disk block size, then we divide it by entry size, then that number should be much larger than we use the block size divided by the record number, right? Yeah, record size, yeah. Yeah, so yeah. Then, now we can when we apply the binary search, yeah, so we can enjoy the performance. Yeah. So we have formula, right? The binary search, the worst case formula. Yeah. The seeding function, log base 2 of n plus 1. This n is the number of index entries. Yeah? Yeah. Number of index entries. N means the number of index entries. Yeah. And then that number is much smaller than the number of data records in the original table. Yeah? Yeah. So we want to make this number as small as possible. Okay? Yeah. All right. Yeah. Yeah. So now you can see the basic properties of the primary index. But there is a condition. Yeah, so don't forget the condition. The condition, the original index field should be ordered in the original table. Yeah. We do not do sorting. No sorting. It is ordered without sorting. We can apply. Yeah. All right. Next, we need to move to the dense index. Yeah. Yeah. All right. Yeah, because the general business data, the chance the rows in the original table are ordered for a particular search field, that chance is very small. Yeah. That chance is very small. Okay? So we need to find the good way if the data is not ordered for the original index field. Yeah. All right, so next, binary search based in indices. Yeah. Now, yeah, look at how to, yeah, because I mentioned we can make prediction. Yeah. The row to be searched for, we want to make prediction on this. Which block, which disk block contains the row to be searched for? Okay? All right. We can use binary search to get it easily. Yeah. Order the files. Yeah. So a table. Yeah. So for the binary search-based index, the first way, the given is ordered. Okay? Yeah. So we use the primary index. Second, if the given data is not ordered, then but in both ways, we make All right. On the index field. An index file is created and the index entry stored in order to apply the binary search. Yeah. So the goal with apply the binary search. Then, if both data file and index file are ordered, why using the index file is, yeah, so here, because sometimes so the people may ask question like this. Yeah. Data file, index file always ordered, right? Yeah, always ordered. But sometimes the data file could be ordered. Yeah, could be ordered. Yeah. But still faster because the size of the index file much smaller than the data file. Okay? Usually the original data file has more fields and contains amount of data. The size is different. Okay, all right. An index file has only 2 fields, key and a pointer. Yeah, it's much smaller. The entry size is much smaller. Yeah. So a larger file uses more disk blocks. Okay, yeah. All right. A smaller file results in fewer disk accesses. Yeah. So that's another reason we can see. Yeah. So even if the same number, yeah. So here, the same number, yeah. Here we can understand in this way. Yeah. Yeah. So here you can see the assumption is original data ordered, right? Yeah. Yeah. But for dense index, yeah. So original data, yeah. So this part, yeah. Not ordered, not if, yes, let me put it if not ordered, then we will use dense index. Okay, dense index. Yeah, so we can handle it. Okay, yeah. So yeah, but if it's ordered, we can still use dense index, right? Yeah, yeah. So here, this question is asked. Dense index. Yeah, but the question is, if it is dense index, you do not save further. Sparse index, you can save more. If you use dense index, you can save, but not as much as the sparse index can save. So here the question you understand in this way. Yeah. 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 Because you didn't skip large number of rows. Yeah. Right. All right. Yeah. Then, so next we need to move to the dense index. Yeah. And the sparse index. But our main focus is on the dense index. Yeah. Sparse, we just completed primary index for the representative of the sparse index. Yeah. All right, some comments on primary index. Yeah. So before I move to the dense index, yeah. The idea is very simple. Yeah. Idea is very simple. Yeah. But before I topic, yeah, I want to clarify, make some comments. The primary. All right. The first comment, yeah, because we do not have much time at this point, I just want to complete this slide. Then the discussion for the dense index we can leave to next time. Yeah. Next week we will have 2 classes. The first class we complete several problems. Remaining problem we complete. But the second class we need to do review for the final. Okay? Yeah. Review for the final. Yeah. All right. Yeah. Here, the first comment. I want to emphasize the primary key, our old primary key, okay? Yeah? So the primary key of a table, of a SQL table, is different from the primary key of a primary index. Do not get confused, yeah, because inside primary index we use this phrase, primary key phrase, yeah. Then people may get confused, yeah. Actually, I saw some technical authors, they got confused. Yeah. Technical authors, when they write technical articles, they got confused. Yeah, I saw those things. Yeah, all right. Yeah, because this primary keys. Yeah. The special thing is any ordered key can be used as the primary key of a primary index. Okay? Yeah. So it may not be the primary key of the original table. That's the main difference. Okay? Yeah? All right? So any ordered key, yeah? The values key field must be open. Any ordered key can be used as the primary key of a primary index when we create a primary index. Necessary the primary key of the original table. That's the meaning. Okay? So try to tell the difference. Yeah. This is the main point for the understanding. Yeah. Why I emphasize this point out here? Yeah, because I remember when I read an article, just do some online search, read an article, I noticed that author understand differently. Okay? That author said only the ordered primary key in the original table can be used as the primary key of the primary index. Well, because I believe that author got confused from the wording, because from the outside form, yeah, primary key, the primary key there, then equalize these two concepts. So, the right understanding should be like this. That's the first comment. Then the second comment. All right. Then we need to determine the index types. Okay, all right, yeah. All right, so first we select an indexing field. Right, yeah. Then there are two cases. Because in order to do fast search based on one particular field, you want to create an index file on that indexing field. So you need to select indexing field first. Then there are two cases. The first case, the indexing field is ordered. Oh, yeah. Ordered. Second case, unordered. Okay, all right. But the ordered case, usually small chance, right? In general, small chance. Yeah. Unordered, large chance. Okay, all right. Yeah. So if you're lucky, you get the indexing field ordered, then you can apply the primary key or primary index to save as much as you can. Yeah, because you can make good prediction. Okay? You can make good prediction. Yeah. All right. Then unordered, most of the time unordered, then you have to use index. Yeah, we will discuss next time the dense index. Okay? Yeah. You can still save a lot. Yeah. You can still save a lot. Although not as much as the primary index. Yeah, but you can still apply the binary search. Yeah. Yeah. The number of entries, that number relatively large, but you don't worry, right? Right? Yeah. That number is large. Why you don't worry? Yeah. Here, I need to recall multi-level tree structure, right? Yeah. Remember last time I mentioned that multi-level tree structure to store our index entries. Okay? Yeah. So the B tree and a B plus tree. Yeah. B tree, B plus tree. Yeah. Yeah. In this class, I do not want to go to the details of B tree, B plus tree. Very complicated. Very, yeah. Before COVID, B tree, B plus tree. Yeah. Too complicated. Yeah. All right. Yeah. Because when we apply the multi-level tree structure, because we can handle large number of nodes. Yeah. Here, let's talk about the nodes. Okay. Yeah. Large number of nodes. Because that tree, that structure, yeah. Yeah. Because each level, the number of branches in each level you know, dozens of nodes or even hundreds of nodes sometimes. Okay, sometimes hundreds of nodes, sometimes dozens of nodes. Yeah. So then, you know, each level you have that many branches. Yeah. Then you go down. Yeah. Then, as I mentioned last time, usually 4 or 5 levels, you can store billions of nodes. Billions of nodes. Okay, like that. Then you do not worry. 4 or 5, that means you need to do 4 or 5 comparisons. You can find the location of your disk block. Yeah. Disk block. You can find the right disk block in 4 or 5 comparisons. That's pretty good. Yeah. That's very efficient. Yeah. Even if you have billions of rows, you can do that fast. Yeah. So here I just want to convey the point. Even if we use the dense index, we can still do the fast search operation. Yeah. All right, so that's the comments. Yeah. Before we move to the dense index topic. Yeah. All right. Next time, I want to talk about the details of the dense index, but not much details. Yeah. So the dense index, it's pretty much there. Okay. Yeah. Yeah. So we do not have a lot of things to talk about. Yeah. It's pretty much there. Yeah. So we do not need much time in next class for discussion. Yeah. After that, I may like to talk about a few programming coding questions. I haven't completed. I have special methods I use. I want to explain to you, help you understand the code. Yeah. Otherwise, you need to guess. So why you use this way? Okay? Yeah. So I need to do some coding explanation next time. Yeah. All right. Yeah. That's it. Yeah. Just remind you another time. Final 2 weeks from today. Okay. Today Thursday. 2 weeks from today. Also Thursday, December 18th. Yeah. 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 The time 6:55. Yeah. I haven't posted. Yeah. But I will do that quickly. Yeah. 6:55. Yeah. So our regular class time, because we feel more comfortable, right? Yeah. We do not need to make delay 45 minutes. Yeah. Yeah. Okay. Yeah. All right. That's it.